Biostat 6611, skills for the rest of your life. Bootstraps and probability. It's the bread and butter, baby. What's your jam?
Greetings, Bio 6611. In this lecture, we're going to introduce the idea of bootstrap sampling, another avenue to make part of the bread and butter to your jam of your statistical toolbox. We're first going to introduce the motivation and walk through the general concept behind the bootstrap. We'll also finish with some notes of how you can evaluate bootstrap performance before moving on to additional lectures with examples of using the bootstrap in 1 and 2 sample cases. So let's start with the motivation. So far, we've primarily worked with this idea of sampling distributions. And in classical statistics, that's what a lot of our inference is based off of. We assume some distribution for the population we're sampling from, and based on that assumption, we'll derive some relationship to our statistic of interest. For example, recall previously we talked that our sampling distribution of a statistic is the probability distribution we would observe based on random sampling. It is again an assumption of the theoretical underlying distribution that sample to sample will vary. For example, we've already seen in the class a couple different cases of this. We see, for example, that we have the sample mean, which is normally distributed with mean mu and then variance sigma squared over square root of n. We can also note this is exact if we assume that x is sampled from a normal distribution or approximate via the central limit theorem. We also introduced the idea of the statistic, which involves the sample variance and the population variance being chi-square distributed. Likewise, we also have two cases where we can transform either an individual observation x or the sample mean x bar to a standard normal distribution with mean 0 and variance 1. Or likewise, if we don't know that variance, we have a t distribution approximately, which we use for doing the t-test or powering studies. However, what if the underlying distribution is unknown for a given statistic? Either we haven't been taught it yet, no one's derived it yet, or there's just some really funky math going on. How could we possibly estimate then the sampling distribution for a statistic in this case? Or what if we're proposing something that isn't sort of a standard thing like the mean or the variance? In fact, is it even possible to estimate the distribution of a random variable in this case, or are we sort of out of luck? Do we just have to throw up our hands and go back to some of the bread and butter that we know of with the central limit theorem and distributional assumptions? Well, obviously that wouldn't be the right answer, because why would we spend multiple lecture slides discussing nonparametric methods? One solution we can use actually is known as the empirical cumulative distribution function, really focusing here on that idea of empirical. We've of course talked about the CDF previously, but it's primarily been in the context of a defined or known distribution. However, we can still describe the distribution of a sampling statistic based on some random sample of a population. For example, we can plot out the CDF just based on the data we observed empirically, and this will represent our best estimate or guess of that corresponding population distribution, even if we have no idea what the underlying distribution may truly be, or it could be a mixture of different distributions. For example, we see the figure here is a random sample of size 100 from an exponential distribution, but we could pretend we had no idea what that is, or was for the underlying distribution, and we can just plot out the essential CDF here of our curve from 0 up to infinity, or in this case, approximately 4 being the largest value. From this, we can leverage other properties that we intuitively have been using without giving a name to. For example, we have the plug-in principle. If our goal is to estimate the sampling distribution for some statistic, we generally have had to know previously what the underlying population and its distribution were. And again, that could be unknown, and a lot of times it is. We also need to know the sampling procedure. For example, did we sample randomly and with or without replacement from a population? As well as the statistic we're trying to estimate. Is it the sample mean x bar, maybe the variance, or something crazier like the ratio of sample means for two groups? Now, actually, the plug-in principle is a natural and frequent approach we've been using. For example, we don't really, in most cases at least, know what the true mean mu is and the true variance sigma squared is, but we actually estimate that and plug it in with x bar or s squared. Or even to get a little more connecting of these dots, We know that x bar calculated from independent and identically distributed, or IID, observations has a standard error that we can represent by sigma over square root of n. Now, of course, we often don't know the population variance or standard deviation, so we just again plug in that estimator s for the sample standard deviation to get our sample standard error estimate of s over square root of n. So intuitively, we actually do this a lot in practice, even though we don't always explicitly note that this is how we're deriving or estimating these different components. So let's just briefly review some theory we discussed previously. So let's let capital F and lowercase f denote the cumulative distribution function and the probability distribution function for some unknown distribution, which has a random sample of x1 up to xn from that unknown distribution. Without making any more assumptions about that distribution, we can use and leverage this empirical distribution approach, where we simply calculate discrete representations of the function like we saw in the previous slide for the CDF and the PDF with capital F of hat s and lowercase f of hat s. Now, note when we discussed the probability theory earlier in the semester, we calculated the expected value of x for some given distribution, known distribution f, as just the sum of the value of x times the probability or the probability mass function f of x. However, if we don't know or have any idea of that underlying distribution, we can empirically estimate it and substitute those values, which we see below has our calculations for the expected value and the variance. The one little thing to note as well, based on our discussion about the biasness of the variance calculations, that we do technically here have a biased representation of the variance where we divide by 1 over n instead of 1 over n minus 1. So what does all this help us do? This will help lead us into the Bootstrap and intuitively explore what the Bootstrap is trying to accomplish. The gist of it is that the original sample we take, we believe at least, is approximating the population from which it was drawn. So in theory, resamples from this sample should similarly approximate what we would get if we happen to take many repeated samples from the population, like we might wish to do in actual practice, but are usually restricted from doing due to resource or time constraints. What we call then the bootstrap distribution of a statistic, we can calculate that based on many of these resamples from the original sample to approximate the sampling distribution which we don't know of the statistic, and then do inference and evaluation based on that. Again, this resampling will create an empirical distribution which we use as the bootstrap distribution for our statistic of interest. Specifically, this repeated sampling is a technique known more generally as Monte Carlo sampling. And don't worry, we'll break it down in the next few slides, more specifically what the bootstrap means and how it's implemented. So let's sketch out the general bootstrap concept, which I think is helpful to really connect the pieces together. Now on the left-hand side, we see we have first our original sample and a sample statistic. And primarily, this is what we focused on previously. We take some sample or we get a sample of data, we calculate some sample statistic from said data, and then we either do inference off of it, explain the variability based on descriptive statistics or other summaries from that one sample. Now, what we're interested here is actually trying to derive, on the right-hand side, this bootstrap distribution of our statistic of interest. So how do we go about doing this with this idea of repeated resampling with replacement from the original sample? Well, what we can note here is we're going to have to draw a bootstrap sample. And so, for example, let's just assume we're starting with the very first one. And what that means is that from that original sample, we are going to sample with replacement those observations. From that bootstrap sample, we're then going to calculate the bootstrap statistic instead of just the sample statistic. And from this bootstrap statistic, we are then going to derive and combine them into a bootstrap distribution. Now, obviously, at first, we just have one bootstrap sample and one bootstrap statistic. So what we want to do is we want to take a second one, and from there we'll get a new bootstrap sample, calculate a new Bootstrap statistic and then add that to our Bootstrap distribution. And we're not going to stop at 2. We're going to repeat this over and over again until we have some large number of resampled Bootstrap samples, corresponding statistics, and combining them all to that Bootstrap distribution, which we'll ultimately see how we can use to draw inference on the sampling statistics distribution and corresponding estimates of its variability with, for example, confidence intervals. To further illustrate this case, let's look at a simple example where we can enumerate all possible combinations of the population. So let's consider a sample where we have 4 possible values, 1, 3, 4, and 6. The first question we might ask ourselves is how many Bootstrap samples could we possibly come up with, unique different combinations of these values? And again, this is a sampling and a permutation problem, and so we can think if we have 4 observations, how many different ways can we resample with replacement those 4 observations? Well, obviously, that very first value we draw could be any one of our 4 values. So we have 4 possible choices. Now, because we're sampling with replacement, whatever number we drew, we put back into the pool. And for our second number, we could again draw any 4 of the values. For the third, we have the same, 4 possible values. And again, the 4th value of our sample would also have 4 possible values. So again, we're going to have 4 times 4 times 4 times 4, or generally speaking, 4 to the 4 or n to the n number of Bootstrap samples, which in this case, if we write it out or did the math, will be 256 different combinations, ranging from 1111 to 1113, all the way to 6666. With this sampled and universe of 256 different combinations, we can start to answer questions that may be of interest. For example, what is the probability that the mean of our sample is 1? Well, in this case, it's pretty easy to note that we only have one combination where that's even possible, because as soon as we have one value that's not 1, we're obviously going to have something that's at least a little larger than 1. So in this case, we really have, if we write out our 4 spots, only one choice in each one of those positions for one possible combination. That then corresponds to a probability of 1 over 256, because only one of those 256 could possibly have a mean of 1. So a pretty unlikely circumstance. Likewise, we may wish to ask, well, what's the probability in a sample the largest value I observe is 6? In this case, it's a little trickier, but we can note that instead of calculating the max as 6, we can say, what's the probability that the max is less than 6? And then have 1 minus that. The reason this could be thought of as easier is because if we sketch out our 4 choices again, we really know that if we were to write out each of the 4 numbers here that we could possibly have observed, we can't have the value of 6 for any one of them, because obviously as soon as 6 is in the sample, the max value is 6. So what we see here is that we have 3 times 3 times 3 times 3 possible choices, or we can say 1 over 3 to the 4, divide it by 4 to the 4, our 256. Which if we write out, we should get approximately a 68% chance that the max value will be 6. So let's quickly see how we can verify these results in R and also illustrate then this idea of a complete and exhaustive Bootstrap sample. So we start by entering our first line of code at the top here, dat with our just vector of 4 values. Leveraging the expand.grid function, we can then put dat 4 times to recreate all possible combos of sample length 4 or sample size 4 and store it in the object boot, which will be a data frame of all 256 combinations. Then for our first question about the mean, the probability that the mean is 1, we can use the apply statement and then ask R, well, how many times is the mean actually equal to 1? Compare that to our 1 over 256 we calculated before, and we see that these values match. Likewise, for our probability the maximum value observed in a Bootstrap sample is 6, we can use the apply function, margin equals 1 for the rows, calculate the max value, and then ask the self, well, what's the average that the boot maximum boot is equal to 6 versus our calculated probability? And in that case, we see again, we end up with the same probability. So we are able to verify the results from boot, which is our bootstrap distribution of all of our possible samples, which we then stored or calculated from the statistics, either the mean or the max value for each sample. For example, we could also make a histogram of the sample means to get an idea, again, of where the spread is. And what we see here, because, again, it is normal, the mean is approximately normal based on the central limit theorem, we do see we have, first off, a nice sort of normal-ish shaped curve as our distribution. We can also note just the general spread of data and sort of where the expected mean would be based on our sample of 1, 3, 4, and 6. This figure here then represents our bootstrap distribution of the sample means, or the empirical sampling distribution for the sample mean for the set of data. One other thing we can note as well is that we can calculate summary statistics based on our original data set, which we maybe don't want to assume any distributional assumptions on, and the corresponding estimates from our bootstrap distribution. Now, in this case, we can note our original sample had a mean of 3.5 and a standard deviation of 2.08. And in this case, with our exhaustive sampling of all 256 combinations, we can likewise see here that we have the mean equal to 3.5 as well, and the standard deviation, or what we call the standard error of the bootstrap, to be 0.903. The bootstrap standard error of a statistic is essentially going to be the standard deviation we take from that bootstrap distribution of the given statistic. So for example, anytime we calculate SD of the bootstrap distribution, what we're really getting out is the bootstrap standard error for our estimate. Now this leads us to the sort of crux or challenging problem we have. When we have just 4 observations, there were only 256 possible combinations, and therefore we could define the entire sampling space without much of a problem. As n, our sample size, increases, though, we really can't exhaustively explore this universe. For example, if n is just 30, we really have 30 raised to the 30 combinations, or 2.0589 times 10 to the 44. That's just way too many combinations to exhaustively describe and then further calculate summaries on. Luckily, though, we can leverage that idea we've mentioned previously in this lecture of sampling with replacement to estimate our bootstrap distribution. So we can take a subsample of all of those millions upon billions of combinations and then derive the bootstrap distribution and draw some inference off of that. For example, on the bottom of the slide, we've outlined the general steps we'll take, and we'll see in a toy example on the following slides. Given a sample of size n from a population, we're going to draw a resample from that original sample, also of size n, but we're going to do so with replacement from the sample. In other words, every time we draw one value or one row of data, we're going to store that in our bootstrap sample, but also keep it back in the original sample to potentially be resampled or appear multiple times in our bootstrap sample. From this bootstrap sample, we're going to compute a statistic that describes the sample, for example, the sample mean, and we're going to repeat this resampling process many, many times, for example, 10,000. We'll then construct the bootstrap distribution of the statistic. We'll inspect its spread, bias, and shape, and calculate some summary statistics to describe the variability of our statistic of interest. As an example, let's, in this lecture set, look at a case where we know the sampling distribution. So we're going to simulate a size 50 draw from a normal distribution with mean 23 and variance 49. Let's estimate then the bootstrap distribution for the sample mean, which we also know should be approximately normal. So as we always do, we're going to start by setting our seed for reproducibility, and we'll generate that random normal sample of 50 observations. Here in our code, then, we're going to define b, which will be our number of bootstraps we wish to generate and sample. And we're going to then initialize a vector for results, which one nice way to do this as well that we haven't necessarily seen previously is using numeric b, which will create our vector of b length to store our results in. And now here comes the Bootstrap resampling portion, which I think is great because it's a beautiful simplicity and for the amazing power we're going to get from it. We see here we can generate a for loop going from 1 up to however many Bootstrap samples b we wish to do, and we're going to then resample with replacement. So we see this here with our line of x sample, where sample is going to take whatever the object is dat. We're going to draw a resample of 50 observations, and we want to replace the observations so they can be resampled multiple times. Once we have that ith iteration in our x resampled Bootstrap sample, we're then going to calculate our Bootstrap statistic, in this case the sample mean, and we're going to store that in our my.boot object in its appropriate ith indexed location. And once R runs through all those calculations, we're going to have then a Bootstrap distribution to look at. For example, we can draw some conclusions from this simple Bootstrap implementation. First, we can note that we have on our top left panel here where I just drew the star, our population distribution of that normal mean 23, variance 49. Then for a random sample, one of those, our data that we've randomly sampled 50 observations from, we see right below, it also has an approximately normal distribution shape to the histogram. Now, the nice thing about this case is that we do know the actual sampling distribution of the mean. And so here we can note over here we have the population distribution with normal distribution, mean 23. The variance will be 49 divided by 50 because, again, this is the means population distribution. And then what we see below is that we can see how closely this is approximated by our Bootstrap distribution, or the histogram of our 10,000 samples. So we can see it looks generally pretty close. A few things we can note here. The shape and spread of the Bootstrap distribution are going to be comparable to that of the sampling distribution. The center, though, of the Bootstrap and the sampling distributions will be different. Now we can note this is because, in actuality, when we derive the population sampling distribution, we know it's 23 based on theory. However, the Bootstrap distribution is going to be forced to rely on whatever our original sample was. And we know each sample will have its own variability around the true population. And then in and of itself, we're taking repeated samples in our Bootstrap, which also contribute potential variability. So we see here that our blue dashed lines are slightly off-centered from each other, so they're not exactly the same. We can also note, though, we can calculate the bias, or the difference, by looking at the center of the Bootstrap distribution to the observed statistic, or the sample mean we calculate, to summarize how far off we may be based on our Bootstrap sample. And so that leads us to some closing points before we move on to our next lectures to see some actual practical real data examples. So again, let's just briefly define bias in a more formal manner. The bias of some estimator theta hat, so this could again be something like the sample mean, variance, ratio of means, or something else, can be represented as the bias of theta hat is equal to the expected value of theta hat, that theoretical true value, minus then the truth theta. In the case of our Bootstrap, the estimate of the bias is very similarly defined, but we see here that instead of comparing that to the just theta, the true value, we're actually going to compare it to theta hat, the estimate from our sample, and then theta hat asterisk or star here and here represents that Bootstrap sample statistic. If an estimator theta hat tends to over or underestimate the true parameter value of theta, then it is considered biased. And similarly, our Bootstrap estimator can be used to determine if there might be bias in that estimator, or if the bias is 0, we would say an estimator is unbiased. So let's summarize some performance measures and things that we should keep in mind when looking at the Bootstrap and what we expect to see. So for most common estimators under some fairly general distributional assumptions, we can take away the following messages. The first of all, what we saw in the previous slide with our histograms and our theoretical normal distribution curves, is the center. The Bootstrap distribution is not an accurate estimator for the center of the true sampling distribution. Again, in that case it was easy because we knew the truth. But in practice, we don't want to make an assumption about the underlying sample distribution and its corresponding theoretical properties. And so we should just note, in general, it's not going to be an accurate, precise estimator. However, the spread of the Bootstrap distribution will reflect the spread of the sampling distribution, even if the center is slightly biased or off. Similarly, the skewness of the Bootstrap distribution will also reflect the skewness of the sampling distribution. So if it's right or left skewed, we should see that as well in our Bootstrap distribution. And finally, we can leverage the bias to estimate from our Bootstrap the bias of the sampling distribution relative to the real population in our sample. So therefore, with these things in mind, we can note Bootstrap sampling is useful for studying the sampling behavior of estimators. For example, its standard error, its skewness, its bias, and for obtaining confidence intervals for a parameter. However, it is not used to improve estimators or to make us more confident in the point estimate itself. And just the final closing quote to leave you with in this idea, for good accuracy, we should generally have 10 to the 4, about 10,000 Bootstrap samples or more. I have a quote here from Tim Hesterberg in his paper Bootstrap, which is in our Canvas course paper repository you can read more about, where he talks about also some of these trade-offs. And just one final thing to note is that not all parameters will be estimated as well with Bootstrap sampling. It's not, again, like anything in statistics, a single cure-all. For examples, when dealing with quantiles, or any summary statistic that may depend heavily on a small number of observations from the larger sample, the Bootstrap may have more variability than we expect. And so here we'll stop and then move on in our next two lectures to looking at actual applications of the Bootstrap to real one sample and two sample data scenarios.